Students, Mrs. Nielsen here. I wanted to give you a quick introduction to that Gizmos on equilibrium and pressure so that hopefully I clear up anything that might be confusing for you. So let's go ahead and get started. All right, so I thought I'd start out with this picture of a much younger version of myself. This is me scuba diving in Cozumel, Mexico, and I have been a certified scuba diver for most of my life since I was 12 years old. So I don't know if you've ever thought about this, but you can see that tank on my back, and the air that's in a scuba diver's tank is actually the same amount of air that it would fit into a phone booth. Now, I don't know if you all have ever even seen a phone booth in your life, but it used to be an area for privacy where you could make a phone call by paying a couple of quarters. And it was big enough to stand up in. And so you could take all that air and compress it into a tank that fits on a scuba diver's back. And that's enough air for a scuba diver to be able to go down underwater for 45 minutes, an hour, maybe more, depending on the depth that they dive. And the only reason we can do that with gases is because gases have this property where they are compressible. And this is unlike other states of matter. Gases are so far apart that we can put them under pressure and we can push them closer together by decreasing the volume of their container. So if you decrease the volume of the container, you increase the pressure. Now, you'll notice that scuba divers have this piece of equipment here, this hose, and that hose is called a regulator. Okay, it's basically the mouthpiece that fits inside the diver's mouth. And that's perhaps one of the most expensive and most important pieces of an equipment that a scuba diver has, because the goal of that regulator is to take that high pressure from the tank and convert it into a pressure that's okay for your lungs to breathe. Remember, your lungs are used to breathing a pressure right around 1 atmosphere here at sea level. So if we compress all that air, decrease the volume, increase its pressure, if you breathe straight from the tank, you're going to blow out your lungs, okay? And that could be very possibly fatal. So that regulator is a very important job to change the pressure of the gases from the tank so that it's okay for your lungs to breathe safely. Okay. Remember, once again, why do gases exert pressure? Well, this is because gases are in constant, rapid, random motion. And remember, every time there's a collision exerts some force over a unit area, right? And those collisions are what cause pressure. So pressure, once again, is a force per unit area. And pressure can be measured in pascals or atmospheres or millimeters of mercury or torr or PSI, pounds per square inch. There's lots of different units of pressure. But in this Gizmos, you're going to be seeing them use megapascals. MPA stands for megapascals, and that is 1 million pascals. So it's 10 to the 6th pascals. Okay. One other thing to keep in mind throughout this Gizmo is the ideal gas law, right? PV equals nRT. Remember, when you change any one of these variables, you can use Pivnert to help predict what the effects are on any other variable. Okay, so remember when we use this equation, pressure is in atmospheres, volume in liters, N is number of moles, R is a constant, and temperature is always, always, always measured in Kelvin in terms of gases. The other thing you can use as a quick reference is just to refresh your memory, we had that PTV index card that we made, right? So you could always think about that to do a quick understanding of what the relationship might be between pressure, temperature, and volume if one of those is held constant. Another law I want to remind you of is Dalton's law of partial pressures. So remember that whenever you have a mixture of gases, for example, when we collect gases over water like this, the total pressure inside the container is going to be equal to the sum of each of the individual gases inside. Okay, so all the gases that are inside that container are going to each have what we call a partial pressure. And when you add up all the partial pressures, you get the overall total pressure inside the container. All right, so I want to switch gears a little bit and take a look at the gizmo itself. And when you look at this gizmo, things look a little bit different here. I'm going to go ahead and increase the number of moles of N2O4. This is very similar to the gizmo that we did the other day. As a matter of fact, it's the same exact gizmo. We're just using different functions within the gizmo. Okay, so one thing I want to point out is that we're working with particles of gas. Okay, so these are all gas particles that you're looking at in all of these reactions. So notice they fill up the entire container. You have, this is a lid on the container here. Okay, so this lid is right here. You can see. Okay, so this is a closed system. The gases are contained within it. But notice what happens when I increase the number of moles of a substance in there. Oops. Let's try that again. If I increase the number of moles of a substance, look what happened to the size of the container. I increase the number of particles. If that N, the number of moles, goes up, then the volume goes up too, as long as the pressure is held constant. And you'll see what the pressure is at any given time right here at the bottom on the right-hand side. Notice again, the units are MPa, which stands for megapascals. That's 10 to the 6th pascals. So that's the atmospheric pressure that's pushing down on the outside. Now, you can increase the pressure on the outside by dragging these weights over. Oops, let's try that again. So I can take these little weights and put them on here. And notice what happens to that pressure as I do it. See how the pressure is starting to go up? You can drag as many weights as you want over there, all or none. Okay, and notice that if I increase the pressure on the outside, now the pressure is all the way up to 108 megapascals and the volume went down. Those particles are a lot more crowded now. And remember, if they're more crowded, they're going to have more collisions, right? So as long as the lid on that container is not moving, then you can assume that the pressure outside that's given here is equal to the pressure on the inside. In other words, if I just added all those weights to get a total pressure on the outside of 108 megapascals, then that's also the total pressure on the inside. Okay, now you can also see partial pressures in this simulation. So notice if I'm going to take this N2O4 down to 0. We're only going to look at NO2. So right now there's only nitrogen dioxide inside that container. If I click over here on the bar chart, notice I can change this drop-down menu here to show pressure instead. Okay, you want to do that so that you're looking at pressures and not moles and concentration like we did the other day. Click that upward arrow, it'll zoom out a little bit. And then again, you can click the show data values and it's going to show you pressures. So notice that all of the molecules inside the container are NO2, nitrogen dioxide right now. So the total pressure that's shown down here in the bottom is the same as the partial pressure of NO2. Now, if I go back and I add some N2O4 into the container, look what happens. Now, if I click back over to the bar chart, you can see that my number of moles I'm sorry, not number of moles, the pressure, the partial pressures of NO2 and N2O4 are now equal, right? Because I added equal amounts of each one. So one thing to remember here is that it doesn't matter what the identity of a gas is. Its partial pressure is based on the number of moles of that substance, okay? So the identity of the gas doesn't matter. It's all about the number of particles, and because the collisions between those particles are what exerts pressure. Has nothing to do with their molar mass or their identities at all, okay? So that's one thing to keep in mind. Another thing you're going to be looking at throughout this lab is, let's see, let me go back over to my sheet here. You're going to be asked to calculate some equilibrium constants. Okay, and we looked at how to do that the other day with concentrations. Okay, so for example, let's say that I have this reaction between hydrogen and oxygen to produce water. And of course, I want to balance this. Okay, and as it will be in this simulation, you can assume everything is in the gaseous phase. Okay, and we learned how to write equilibrium constants the other day. Remember, we said that Kc is going to be the concentration of products raised to their coefficients divided by the concentration of reactants raised to their coefficients. Okay, and one thing to keep in mind, and I don't think I mentioned this in class the other day, one thing to keep in mind about equilibrium constants is that you never include any substances that are solids or liquids. Solids and liquids never get included in the equilibrium constant expression. And the reason for this is because solids and liquids have a constant concentration, right? The concentration of a substance is moles of solute divided by liters of solution. Well, there's no solute or solvent if you have a pure substance like solids or liquids. So the only things that are included in an equilibrium expression are going to be aqueous substances or gases. Okay, now, when something is in the gaseous phase, we can instead look at its concentration as its partial pressure instead, right? Because again, the partial pressure is based only on the number of particles that are there. It has nothing to do with the identity of that gas. It's only the number of particles and thus the number of collisions. So we can take this one step further, and for gases, we can, instead of looking at a Kc, remember this C stands for concentration, we can now look at something called Kp, the equilibrium constant for pressure, right? Or partial pressures. So I can say that it's the partial pressure of products raised to their coefficients divided by the partial pressure of reactants raised to their coefficients. Okay, so you might be asked, or you will be asked actually, to create or calculate KPs as a result of some of the measurements in the Gizmos. And so you can do it with their partial pressures. Now, once again, I want to remind you that when it comes to finding the partial pressure, you want to come over to the bar chart, click on the pressure from the drop-down menu. If you need to adjust, you can use these arrows, and then the partial pressures are shown right above the bars there. Okay. Last thing I wanted to do was just go through the student exploration worksheet with you. I want to just point out a couple of things. So let me just quickly go through here and make sure that everything makes sense. Let's firstly just want to look over the learning objectives. You should be able to observe partial pressures always sum to the total pressure of the system. That's Dalton's law. Determine the equilibrium constant, Kp. I just pointed that one out to you, right, Kp. Kp does not depend on initial partial pressures. Just like we looked at with concentrations the other day, you can change the initial concentrations and pressures all you want. It doesn't affect the equilibrium position. The only thing that'll affect the equilibrium position is temperature, and we're going to look at that one next week. You're going to be able to calculate a QP exactly the same way as I showed you to calculate reaction quotients the other day. You can predict the direction of a reaction based on the identity or the values of Q and K. In other words, remember, Q is always not at equilibrium. K is at equilibrium. And so if Q is less than K, it's going to shift to the right and produce more products. If Q is greater than K, it's going to shift to the left and produce more reactants. Okay, and that should hopefully get reiterated throughout this unit, and it'll become a little bit more second nature to you. Lastly, predicting the effects of changing pressure on a mixture of gases at equilibrium. Okay, so I'm going to scroll through here, make sure you should be able to do all of this, I think. Here, you're going to have to run quite a few different trials and average the results once again, like we did the other day. Here, we're showing the relationship between Kp and Kc. Very, very similar. It's just P stands for pressure of gases instead. And then let's see here. Down here, at the bottom where it starts talking about what happens if you change the overall pressure. Okay, so once again, let's take a look at the same reaction. We had hydrogen plus oxygen yields in a reversible reaction, 2H2O, and everything's in the gaseous phase. Coefficient of 2 here. All right, so if you have this system at equilibrium, what happens if you increase the pressure on the whole system? Well, remember, all of the reactions have to do with collisions, okay? So when you get a collision, if that collision between particles is favorable in orientation and has sufficient energy, then you're going to get a reaction. So when we look at changes in pressure to a system at equilibrium, you want to look at the overall number of gas particles, okay? And when you change the pressure, changes in pressure affect gases only. Okay, that's important to remember. We're going to look at this a lot more next week too with Le Chatelier's principle, and I'm just kind of front loading your brains a little bit right now with Le Chatelier's principle. But when you change the pressure, you always want to shift. It'll shift to the side with accordingly. So in other words, here on the reactant side, I have 3 gas particles, right? 2 hydrogens and 1 oxygen, and on the product side, I have only 2 gases, just those 2 water molecules. And so what happens if you increase the pressure on this system, the molecules get crowded, and gas particles don't like being crowded, right? Just like humans, right? We don't like being crowded. So if you increase the pressure on the system by decreasing their volume, the gas particles start colliding more frequently. And remember, anything that causes more collisions will increase the rate of that reaction. So in other words, look at what happens here. If you increase the number of collisions, it's going to favor the side with fewer gases, because the side with fewer gases will have fewer collisions. So decreasing the volume or increasing the pressure on a system of gases will always favor the synthesis reaction, because a synthesis reaction is making less overall moles of substance. Okay, so that's something to think about. And you can always check your work in the Gizmo. The way I would check my work with number 6 here is just set up the system to have 2 hydrogen 2 moles of hydrogen and 1 mole of oxygen and 2 moles of water, and then go take a look at the bar chart and click play and see what happens to the relative amounts of each substance. Do you end up getting more water, or do you end up getting less water, right? You can check it. Again, remember, use those weights to help increase the pressure on the system, all right? So I'm going to let you guys go ahead and play with the gizmos. Again, I'll be available all day, Thursday and Friday, except during my appointment. So if you have any questions for me, just shoot me an email. We can jump on a Zoom together, and hopefully that was helpful. And hope you guys are well and have a great weekend. I'll see you next week.